to be here giving this talk. So it's a 45-minute talk, and I think that's just perfect. I think 45-minute talks are the best, and I promise I will be relaxed the whole time. I will finish on time, no problem, and feel free to interrupt with questions. It's all going to be good. 45. I'm being serious. It's great. So yeah. So this is homotopy theory with applications to arithmetic, I guess. So it fits in the theme of the conference. So what is Artin reciprocity? Well, Artin reciprocity is something in number theory, and it has to do with the construction of what are known as Artin maps. And these Artin maps are attached to fields, so attached to either a finite field, a local field, or a global field. So in all cases, I'll call the field F. So finite field, of course, you can think of FP. A local field, you can think of QP or the real numbers. And a global field, you can think of Q. Or more generally, you can take finite extensions of any of these. And there's also some characteristic P ones. So that's wait, oops, I accidentally pressed a button. Yeah, I probably didn't do anything. The Artin map always has a target, which is the abelianized absolute Galois group, or the Galois group of the maximal abelian extension of your field F. And then it has a source called the class group, whose nature kind of depends on which case you're in. So, so CF is, well, it's just the group of integers if F is finite. And it's the group of units in your field, multiplicative group of units in your field if F is local. And then the most interesting case, when F is global, you take the adels of F, invertible adels modulo units in the global field embedded diagonally. So these adels are kind of built from all the different possible completions of your field, both Archimedean and non-Archimedean. You stick them all together in a certain way, and you get a big ring called adels. Has a lot of units, and some of them come from the global. Those you mod out by. So the Artin maps are natural homomorphisms that you can construct from these class groups to this abelianized Galois group. And of course, it should satisfy certain properties, which pin it down uniquely. So it's pinned down by so first there's kind of a functoriality in F. Well, I don't want to be too precise about all this, but there's kind of two kinds of functoriality. There's one within a given class of fields. So if you have a finite extension of global fields, then you can write down natural maps, in fact, in both directions on both sides, and then the diagrams should commute. So the Galois group of a finite extension is a subgroup of the Galois group of the lower guy. That gives you a map this way. There's also a transfer map backwards. It's quite simple to write down maps going both directions on CF as well. And every diagram that you can write down commutes. There's also functoriality relating the different kinds of fields. So for example, global and local, well, if your local field arises as the completion of a global field, then well, this F cross here is sitting as one of the factors in this adel ring, and you just restrict and you write down a diagram and it commutes. And then there's, for this relating to this, well, the sort of unramified part of this is exactly controlled by the Artin map for the residue field. So anyway, I don't want to be too specific about this, but it's just very natural diagrams you write down and they all commute. And then you have to choose some normalization. And there's actually this system of maps with such functoriality is actually so rigid that there's different ways to normalize, and they're all equivalent. You could choose, for example, that for F finite. So the Artin map for F of 1 in the integer is some Frobenius. So some Q power Frobenius, where Q is the order of the finite field. So what is this? Why do you care? What is this giving you? Well, for one thing, I guess it's doing two things. One thing is it's constructing elements in the abelianized Galois group of these fields. That's not so interesting because in fact, already just these Frobenius elements give you all the elements you need, but more importantly, it's providing relations between these elements. So it's saying that any relation you see in these groups will also be reflected in the absolute Galois group. And the most important one is this. When you mod out by F cross, that's a relation you actually see in Galois theory. And so, for example, if you choose a prime P and consider the quadratic extension Q adjoins square root of P, and then you act by everything you get from this story, you very easily derive the quadratic reciprocity law from elementary number theory. From the fact that these guys, F cross, give you relations. So that's kind of what this is. And what do I want to do? So goal is to give a uniform construction. Sorry? Write even bigger? Yeah, sure. Give a uniform construction of these maps. But well, as uniform as possible, kind of given that the definition of CF was piecemeal. So you'll see what I mean by that. Okay, but I want to introduce just for the purposes of this talk, I want to simplify slightly. So note that, well, this abelianized absolute Galois group, it's a profinite abelian group, right? And every one of those is just a product of its L primary components for all primes L. And we're trying to map to this guy, so we might as well fix a prime L and map to this guy instead, because it's just a product. And I'm gonna only take.
Question, is the definition of CF necessarily case by case, or is it because you chose for the purpose of this talk?
Well, one of the things that comes out of what I'm going to explain is that you can give a non-piecemeal definition. Yeah, you'll see later. So only take those L prime to characteristic of F. Well, when characteristic of F is P, I'm going to throw out one component from this, just for the purposes of this talk, to simplify the Of course, the most interesting case is number fields, and then I'm not throwing anything out. Those are characteristic 0. Okay. So what I want to do is I want to put the logical structure of the construction, I want to give that right now, even though a lot of the terms I use will be undefined and potentially unfamiliar. And then in the rest of the talk, I'll go through and explain what everything means and how it all goes. But I think it's helpful to just have the logical construction first. So there's a step 0. I call it step 0 because we're not really going to do this step. Actually, it's just a fact that we're going to take for granted. So there is it's a serious fact from number theory, which is that if for any of these fields, so F finite, local, or global, then the virtual Galois cohomological dimension of F is less than or equal to 2. So this is if you look at Galois cohomology of your field, it turns out there's no, of some finite extension of your field, that's what was allowed by virtual, then there's no HI for I bigger than 2. This is a serious fact from number theory, which we have to take for granted to make the method work. You'll see exactly why. And yeah, but it's all we need kind of from traditional number theory, so to speak. The rest will be sort of something new. So then the first step is then a fact that you can deduce just from this hypothesis. So if F is any field with a virtual cohomological dimension at the prime L less than or equal to 2, then there's a rather strange expression for the abelianized absolute Galois group of F. Exactly the target of but we want to be the target of our Artin map. So it's going to be a pi1 group of some spectrum, which will be some version of a dual to the algebraic K-theory spectrum of F. What? Yeah. Thank you, Peter. Yes, implicitly, I'm L completing everywhere. So, and there's also an implicit L in this guy. We're working at the prime L from now on. Yeah. So again, I'll explain more what all this means, but okay. And then the second, has to do with the right-hand side, so to speak. Then there's something to do with the left-hand side. It's also related to K-theory in a different way. So if F is finite, local, or global, then there is a canonical map from CF to a different K-theory. So not K-theory of F, which implicitly is like K-theory of finite dimensional vector spaces over F, but K-theory of arbitrary locally compact abelian groups with an F module structure. And I'll mention that Arndt and Brownling showed that this is an isomorphism. So indeed this thing can be taken as your alternate definition of a class group, and it's not at all piecemeal. Okay. And then the third step, oops, yeah, maybe well, it's hard to decide about the shadow versus well, okay. I'll just try to not write through the shadow. So the third step, which is, what? I can't, because then it'll be off the screen for the people in Toronto. Yeah. Well, I could, but then someone was complaining about not. Yeah, now the poor RAM and my poor brain is gonna have to deal with too many variables. Okay. Yeah. Well, right, I'll be more specific about it later. Locally compact F modules is the one. Oh, sorry, the question was, could I say what this is? And the answer was yes, but not precisely right now. Right, okay. So, yeah, so this is actually where the spheres are gonna come in, although it won't be obvious from the way I phrase it now. So this is that there's a canonical class. I'll call it little j in, well, I'm writing pi0 very faintly. No, I do the dual construction of this K-theory, and then I take this locally compacting for my base ring. So I assumed everything's living over this ring Z bracket 1 over L, universal ring where L is invertible, L prime to the characteristic of F. And all I really need is that you have a class in pi0, but I kind of want to emphasize that you have a canonical point set level construction, so to speak. So it's not like you calculated this pi0 group and point to an element. You really honestly construct something on the nose. Right. And then part 4 is you put it all together to get your Artin map. And this is just some simple diagrammatic nonsense, which I'll just do right now. Well, I have to tell you a little bit about this dualizing thing, but not much yet. All I'll tell you about it is this thing dk1. It's just defined as a mapping spectrum from this to some other spectrum, which I'll denote, which is some dualizing spectrum, which I'll denote omega sub k1. But so what I've just said is that we can equivalently view this J construction as a map of spectra like this. That's just how I'm going to define this duality operation. So there's nothing there. And then, well, this was for this universal base, but if we're interested in a given field, well, actually, for any ring, over Z bracket 1 over L. So we don't need to have a field anymore or anything. We can look, there's a forgetful functor from locally compact A modules to locally compact Z bracket 1 over L modules. So let's forget. And then we can just compose and we get a map like this. But now that we're here, well, yeah, now that we're here, we can take, I guess A op, I don't know. Maybe I shouldn't have tried to do this generality. I'm gonna get confused about A versus A op. But if you have forget it. Let's pretend it's commutative. It doesn't have to be, but just pretend it's commutative. Then if you have a locally compact A module, you can tensor it over A with any finitely generated projective A module, and you still get a locally compact A module. So you have an action map like this. So, and when you compose here, you get a long map like this, and then you can jump by a junction, move this one over to the other side, and what you get, that's equivalent. That long map is equivalent to giving a map from KLCA to dual of KA. And then if you look on pi 1 and take A equals F, well, you have CF mapping here, and then you have pi 1 be K1 KF. That's the abelianized absolute Galois group by 0.0 and 0.1. This was 0.3. And look, we did it. Okay. And you'll have to take it for granted. You'll have to trust me when I say that verifying these properties is actually quite straightforward. All of the functoriality and normalization is more or less obvious from the construction. So, well, I could stop right now. That would make it a 15-minute talk, but maybe, are there any questions at this point? What is LCF? So the question is, what is LCF? And it's the category of locally compact F modules, but I'll explain that in more detail in just a second. Yes.
Before all of this, the normalization that goes for that finite cell only determines the map for finite fields to the order of all fields. And is it true that now with your new stuff, you'll determine it all?
No, this plus this determines it for all fields. That's just some abstract argument in number theory. Oh, the question was, the question concerned the reasoning behind why normalization just for finite fields actually normalizes it for all fields. And it's just because of the strength of this functoriality.
I think that's
yeah, fields?
Hi,
Yeah, go ahead.
Could you just repeat 4, just like, again, just the whole thing, just all of 4?
Sure. So we first used 3. So I say J is a canonical class in DK1K of this guy, but then I'm telling you right now that the definition of this DK1 is that it's a mapping spectrum from this to some other spectrum, which I denote omega K1. That's all you need to know about D, okay? So that means that this is the same thing as just, I'm saying there exists such a map in 3, it's equivalent. So that's a map with this guy as the source, but LC, look, take A equals F. I don't know why I just wanted to point out at this point, you don't need, for this argument, you don't need anything about F. So and then we have LCF, locally compact F modules, but because we assumed we're characteristic prime to L, there's a forgetful functor from locally compact F modules to locally compact Z bracket 1 over L modules. I'm telling you now that that induces a map on K theory. Now we take this J and we compose it with that forgetful map. And we get this diagonal map here. But now here, once we're at this level, we have more structure because now we can act by finite dimensional F vector spaces. We can tensor over F with a finite dimensional F vector space if we have a locally compact F module, and we'll still have a locally compact F module. That's just because this is an F linear category, basically. And that gives on K-theory spectra a map from KF tensor KLCF to KLCF. Now I compose with that again, and I get a map from this tensor product to the same dualizing object. Now I adjoint this one over, so I view this now as a map from KLCF to the dual. That's again just the definition of the dual of KF. I look on pi1, I combine with the previous points, and I get an Artin map. Was that sufficient?
Okay. Yes.
Yeah. All right.
Sorry, I have another question.
Yeah.
My question is which of those, I guess, 5 steps has like the real arithmetic content about, especially about global fields? Because it seems a lot of those are just general for some general field, or at least any field that has the right cohomological dimension. And I'm guessing somewhere in there is hidden like the key arithmetic. 2. So then I guess you're saying that sort of for any field, there's a general notion of class field theory where you define CF as pi1 of K LCF.
Yeah, but we'd also have to define GF ab as pi1 of DK1 KF. I mean, so, which is not stupid. It's kind of like an GF ab is like Galois homology, first Galois homology of GF, you could say, of F, and that the right hand side actually behaves like a tall K homology in some sense. So, but yeah, but yes, 2 is the only place where you kind of seriously use that you have a global field.
And also just with the definition of LCF, is there an obvious functor either from LCF to vector spaces over F or vice versa?
No. Well, yeah, yes, but depending on which situation you're in, it may be trivial or not. It's best for me to address that question when I get to explaining step 2.
Thank you.
Okay. Other questions? Okay, now you get to silently watch me erase the boards. No, I'm not using those. I don't want to get confused. See, I already forgot to put this back up after it. Okay. Okay. All right. So let me start explaining these points in more detail. So point 1 has partially to do with this DK1 operation. So point 1 was about this. Point 1 was about this DK1K of F. And I think to start to explain a little bit about this duality, I want to remind you of some fact about spectra. So we're working with spectra here.
Can you start writing the other word from the top?
Further complaints can be submitted to me by writing. My address is 104 Autobahnbrücke. Anyway, right. So starting with step one. So I want to just say something about spectra and how it's different from the thing it's analogous to, which is the unbounded derived category of abelian groups. So, okay, they're both co-complete stable infinity categories generated by a single object. Here it's Z, and here it's this thing called the sphere spectrum. They have tensor structures for which these guys are the units. They look very similar, but well, also when you rationalize, and you take DZ rationalized, you get the same thing. And it's this purely algebraic thing, which is the derived category of Q vector spaces. So this is essentially because of Serre's theorem on finiteness of stable homotopy groups of spheres. So they only really start to diverge when you start looking at torsion, spectra, and abelian groups. So what happens now when you take a spectrum or an abelian group and you want to look at its like L torsion? Well, a natural thing to do is to mod out by L and investigate that. And over here, something very nice happened. This is the same thing as base changing X to the finite field FL, and it lives in a derived category over a field, and you can't get much simpler than that, right? You've linear algebra over a field. What more could you want? It's as simple as can be. Whereas over here, you mod out by L, well, it's still a mess. It doesn't behave like working over a field. And one way you can measure that it doesn't behave like working over a field is this magical fact that you get an extra operator called V1. Well, actually, it's a map from some shift of this to itself, but that doesn't matter. It turns out when you take any spectrum and mod out by L, you get a canonical new thing you can mod out by, and that's called V1. And that expresses the fact that even when you mod out by L, it still doesn't feel like you're working over a field. And so here we inverted all primes. And now we're saying if you mod out by L, there's an additional thing you could either mod out by or invert and simplify the situation even further. So there's this functor called K1 localization, which you get basically by, well, doing this mod L to the n for every n, inverting this V1 operator, and then collecting it up to get something integral, or at least L-adic. So here, when you invert everything, you get something purely algebraic. Here, you mod out by L, you invert the thing you get. This guy is not purely algebraic, but we can still calculate it. This is the golden zone right here, where in algebraic topology, it's not pure algebra, so that's good. It's kind of like topology instead, but we can still calculate everything. That's awesome. If you try to go to K2, there are people who can do things, but I'm not one of them. But this is the golden zone where you're getting interesting new topological information, but you can still calculate everything. So that's great. Okay, that was a little background. Now, I want to state a theorem of Thomason, which connects this operation to algebraic K theory. So if F is any field with virtual cohomological dimension at the prime L finite, then if you K1 localize this K theory spectrum, you plug in not just F, but any finite separable extension, or I guess you could say any finite étale F algebra, values in spectra. This is an étale hyper. And never mind what that precisely means. It's a form of étale descent, but how do you interpret this? So this means that if you take LK1K of F, you can get at it in some sense just by knowing LK1K of the algebraic or well separable closure of F, and then taking its Galois cohomology of that. the Galois cohomology, the Galois group acts on there, you take cohomology with coefficients in this guy, morally speaking. So that's how you should think of this. So the K theory of your field F is a mixture of Galois cohomology and the K theory of the separable closure. Once you K1 localize, once you perform this simplification. Okay. But to make this truly useful, we have to know what this guy is. Thankfully, there's a theorem for that too. Suslin. So if F is separably closed, then you look at LK1KF on homotopy groups, it's just, well, 0 if star is odd, and it's a Tate twist, ZL star over 2 if star is even. So as abelian groups, it's just 2 periodic, ZL in every even degree, but if you remember the Galois action, if it's cyclotomic, and the twist, precise twist depends on the even degree that you're looking at. So, well, if you combine these two, you get that if the cohomological dimension at L of F is less than or equal to 2, then if you look at pi minus 1 of this KF, this is a funny thing that this operation does, because this V1 actually shifts degrees. That this thing will actually input negative homotopy groups, even if they didn't exist before. And in this case, you get, well, H1 coefficients in DL, which is just continuous homomorphisms from DF, say, abelianized to DF. And this is just because if you look at the spectral sequence, the only thing that can possibly contribute to this degree is this H1 of the degree 0 part of this. And that's exactly what you have. And now you'll have to believe me that something magical happens when you dualize, that even if you only assume virtual cohomological dimension less than 1. So this is not true for virtual cohomological dimension less than or equal to 1, but somehow magically the dual statement is true, even in that more general case. And I haven't told you what this dual K1 is, but so when you dualize, a -1 turns into a +1, and this goes to get that. And I'm not going to explain the precise mechanics behind how that goes, but it's really just some dual version of the story here. So, okay, so that was kind of the Galois side, the target of the Artin maps. So now let's talk about 2, which was this CF going to K1 LCF. So when I wrote KF over here, that's the algebraic K theory of a field. But what it really is the algebraic K theory of the category of finite dimensional vector spaces over a field. That's the input to algebraic K theory of the field. But this K theory machine makes sense for more than just categories of finite dimensional vector space. It makes sense for any category in which, for example, you have a reasonable notion of short exact sequence, any exact category in the sense of Quillen. And now we're going to look at LCF, which is the category of locally compact F modules. So just locally compact abelian groups with a linear action of F. Yeah.
There was a question from the chat
about
what duality you actually mean.
No, I haven't said yet.
I know.
Other questions? I've told you all you need to know for now.
Okay.
So trust me. And then we're going to look at K theory of this. And I'm going to produce, well, I guess I'm writing the same thing twice. So a map from CF to pi1 of this. And again, now we have to split up into 3 cases, right? Because the definition of CF was split up into 3 cases. So we can't do this uniformly. So case 1, the simplest case for this construction is actually not when F is a finite. It's when F is a local field. So, well, then F itself is a locally compact F module. But it also has automorphisms given by multiplication by units in F. And when you pass from this category to K-theory, this gives you a homomorphism from F cross to pi 1 of the K-theory LCF, well, based at the point corresponding to this object. Really, but then by just shifting using the group structure on K-theory, that's the same thing as pi 1 of K-theory LCF based at 0, which is the natural base point for this spectrum. So, and that was CF. So in the local case, you just look at this single locally compact F module with its natural F cross action, you get your K1 class. Nothing going on. So now we're going to move to the finite case, and here's something interesting happens. We're going to again look at F, but something funny will come in. So now I have to tell you something. So look, we have low compact F modules. A special case is any discrete F module. There's lots of those. I didn't say finite dimensional, I said any discrete F module. That includes in there, but also any compact F module. Just the kind of Pontryagin dual to this one. Also includes in there. You can take K-theories. And the interesting thing that happens is that these K-theories are 0. And this is because of something called an Eilenberg swindle. Because if you want to prove that, say, an object X is 0 in K-theory, you can write it as the kernel of a map from a direct sum of infinitely many copies of X. To infinitely many copies of X, or you shift. You can shift and then delete the first entry or something. Make it a surjective map where the kernel is X. And then in K-theory, this is a short exact sequence, so it shows that this thing is equal to this thing minus this thing. But on the other hand, these two things are the same. So you're getting X equals Y minus Y, so X equals 0. And because this is a functorial proof, it's functorial in X, you actually are showing that the identity functor induces the 0 map on this spectrum, which means that that spectrum is 0. And you can do a similar Eilenberg swindle over here with infinite products instead of infinite direct sums. Product of compact things is still compact. So now what can we do? Now we again look at F in LCF. And now we look at its induced class in K-theory. Well, then this is 0 for 2 different reasons. One is that F is discrete because it's finite, and one is that F is compact because it's finite. It lifts here, so it's 0, but it also lifts here, so it's 0. And we have 2 different reasons why something's 0. That means we have a loop. That means a class in pi 1, KLCF. And that will be the image of Z, image 1 in Z under our Artin map. To specify the Artin map, we just need to know where 1 goes, and that's where it goes. And the last case is the most interesting one. So if F is global, so let me remind you that CF in this case is Adels in F, units in the Adels modulo F cross. So I should first produce a homomorphism from AF cross, and then I should prove reciprocity. I should prove this non-trivial statement that it's the zero map when you restrict to F cross. So, well, we can again just look at the Adels of F. Well, we can look at the Adels of F as a locally compact F module. And again, it's a ring, it has an action by the units in the Adels. And just as in the local field case, this gives you your required homomorphism. So, where does the reciprocity come from? Why is this homomorphism trivial when you restrict to F cross? Well, it comes from a very basic fact about these Adel rings, which is that your field F sits discretely and co-compactly in the Adel ring. So this is just like Z sitting inside R with compact quotient. So there's an analog of this for any number field, and it's this. So this is discrete inside here, and the quotient is compact. And now, most of these actions by invertible indels don't respect this short exact sequence, but the ones that come from F cross do. So if you're multiplying by something in F cross, it extends to an automorphism of this whole short exact sequence. And then in K1, this is the sum of this and this, but this is zero because this is discrete, and this is zero because this is compact. So you prove that this factors through AF cross mod F cross. Oh, darn. That's because these ones respect this short exact sequence, which prove that this guy is K theoretically trivial through this Allenberg-Swindle argument. And the last thing to explain, I don't have time for, that's okay, is the canonical class. So well, I'll just say a couple of words about it. So this 4 was this J, and now I'll finally have to tell you what this dualizing object is. Locally compact Z bracket 1 over L modules. Mapping to omega K1, and some kind of K1 local dualizing object. And I define it like this. It's a funny definition, but I define it as the K1 localization of pick S, which is also the same thing. We're working out a prime L, pick the L-adic sphere. Pick means invertible modules over that range spectrum. And in these cases, every invertible module is just a shift of the unit, which is the sphere spectrum. And this is a spectrum which is in fact very closely related to the sphere spectrum, maybe more close to the suspension of the sphere spectrum. It's not equal to it, but it's very closely related, and actually the distinction is wiped out by this K1 localization functor. So you can think of it as just the suspension of the sphere spectrum, but this is the natural target. And what does this mean to have a map out of K theory? Well, in general, what it means to have a map out of K theory, this K theory I said is built from this category. So you should be able to express it in terms of something going on with this category. And it means that if you have any object in this category, then you get, and then I should say actually the construction lifts to pick, the construction exists before you K1 localize. So it actually exists on this level. So to any V, you can associate something I'll call S to the V, which is an invertible as L module. And it means that if you have a short exact sequence, So 0 V prime goes to V, goes to V double prime in here. Then you get a proof that SV is the same as SV prime tensor, SV double prime, and then etc. Meaning you have some higher homotopies if you have longer filtrations of an object, and so on and so forth. So in some sense, it's something concrete. I'm telling you, you can make an invertible sphere, an invertible spectrum, aka a sphere, from any locally compact Z bracket 1 over L module. And well, for a finite dimensional real vector space, there's an easy way to do that. You have a real vector space, you compact 1-point compactify it, you get a sphere. It's funny that it exists more generally, and that's, I think, all I have time to say.
Thank you. Are there any questions for us? Great.
What happens when L divides characteristics?
Well,